Hello, everybody. This is a very short summary for one of the papers that Shafiq asked us to do for the journal club. So because anyway, we are doing the journal club from a distance, I thought of recording this paper and sharing the recording with you. So if you are interested more in more details, then we may discuss this in our coming journal club. Otherwise, I will be talking about a different paper. So this paper is about the electronic correlation in twisted bilayer graphene. So let me start very briefly to show you the motivation behind this paper. So the basic reason is in twisted bilayer graphene, as you might all know, that there is superconductivity and a correlated insulators. And the phase diagram of twisted bilayer graphene, the relation between superconductivity and the correlated insulators, are in many ways similar to the cube rates. And in cube rates, superconductivity is in fact unconventional superconductivity, meaning that the order parameter is not the correlation between electrons and is not the coupling between electrons and phonons. Now, the basic precise question is superconductivity conventional or unconventional in twisted bilayer graphene? Is it really conventional or unconventional? So far, in the twisted bilayer community, the method that is used to answer this question is using this fact that conventional superconductivity gets stronger if the Coulomb interaction gets weaker. So in other words, superconductivity increases as the interaction between electrons get screened. So basically, this is a question of the role of screening in the superconducting case in twisted bilayer graphene. Now, what is screening what? So what is this experimental device all about? So the device is the following. This is a complex heterostructure. We have graphite. These are two graphite gates. This is a boron nitride. This is twisted bilayer graphene at the magic angle. This is thin hexagonal boron nitride. This is a normal bilayer graphene, an AB stacked bilayer graphene. This is another hexagonal boron nitride. Now, what is screening what? So, in fact, we are after the question of seeing what is happening in twisted bilayer graphene. So we need to screen electrons in the magic angle twisted bilayer graphene. And this screening is happening because of the electrons in normal bilayer graphene. So if bilayer graphene is in the conducting mode, then electrons in bilayer graphene will screen the electronic interaction in twisted bilayer graphene. This is the schematic cartoon, and this is in fact more schematic that shows the electric circuit. We can see that there are in fact three gates now. We have bottom, we have top, and we have intermediate. Basically, so far we have seen, and previously we have seen top and bottom gates, but now we need this additional gate to control more parameters. For combination of these three external parameters, they can control four key parameters, which is the amount of carriers in bilayer graphene, the amount of displacement field in bilayer graphene, and similarly the carriers and displacement field in twisted bilayer graphene. So in this experiment, these are the four controlling parameters. Okay, now we know what is screening what. Now we go and ask, when do we screen? So in fact, this is a schematic cartoon of the band structure of the bilayer graphene, normal bilayer graphene. If the chemical potential is in the gap, then we say bilayer graphene is insulating. If the chemical potential in the conduction band or in the valence band, then bilayer graphene is conducting. If bilayer graphene is conducting, then we are screening. If bilayer graphene is not conducting, then we are not screening. In this phase diagram of the bilayer graphene, normal bilayer graphene, this is the amount of carriers and the displacement field. We can see bilayer graphene is always conducting unless we are along these two features, along this red feature here or here. Okay. Now, what happens if we are not screening? This is the normal experimental things you would see in any other paper. So we are in this case, we are not screening. And this is the resistance for twisted bilayer graphene, while this is the amount of carriers in each unit cell. We can see there are small peaks and large peaks, but we can see there are resistance peaks at the integer fillings in twisted bilayer graphene. We can also see some superconducting region close to filling of 2 holes per unit cell. So far, so good. These are all old results. Now, the interesting thing is once we go from the insulating case to the conducting case, once we turn on screening. So now what happens for screening? So this is the conductance of twisted bilayer graphene, and this is the behavior with temperature. These plots are used to extract the gap at the correlated insulators. These 3 traces are for 4 or 3 situations in bilayer graphene. The blue is when we have no carriers, 0 carriers when we are in the gap, and green and red is once the amount of carriers in the bilayer graphene is changed. Once we go gradually to the conducting states, once we go to the screening regime. From these plots, the amount of the gap is extracted and is plotted here as a function of the amount of carriers in the bilayer graphene. We can see if we have 0 carriers, if we are in the insulating state, we get some gap. As we add more carriers, the gap decreases. More carriers means we are getting into the conducting state of the bilayer graphene, means we are increasing the screening. Very clearly, you can see as we add screening, the gap decreases. So more screening, less correlating insulators inside. And this is expected because correlated insulating is because of the interaction between electrons. Now, if we screen the interaction between electrons, we would expect the strength of this correlated insulator to be weaker. Now, this is expected. And we go to superconductivity. Now, what happens in superconductivity as we increase the screening? Okay. This is resistance in twisted bilayer graphene. This is the amount of carriers. These are 2 traces. One trace is for 0 carriers in the bilayer graphene. The other trace is when we are in the valence band of the normal bilayer graphene. One very noticeable feature is the range now where superconductivity occurs for the screened state is large. See, red trace means we are screening, blue means we are not screening. First of all, we can see that this is an indication that the superconducting range is increasing as we decrease the screening, as we increase the screening, sorry. We can see this in another way by measuring the dV/di as a function of the DC current. 2 traces, one is for screening, one without screening. We can see for screening, the range for superconductivity really increases. That's interesting. Now, the last thing is the behavior as a function of magnetic field. So this panel is when we are not screening. This panel is for the screening case. This red is when we are insulating, correlated insulator. This dome is for superconductivity. We can see without screening, the superconductivity dome is small. It gets larger as we increase the screening. Very interesting. Now, this is very clearly shows that more screening, more superconductivity. Now, one last slide more about superconductivity. You can see 4 panels, and they have a common x-axis, which is the carriers in the bilayer graphene, the normal bilayer graphene. First is the conductance. This is typical. If we are here in the gap, no carriers, then we basically get 0 conductance. Then as we increase the carriers, we get more conductance. Now, these 3 panels are for twisted bilayer graphene properties. First one is the critical current, critical temperature, and the range of superconductivity. First, the critical current. We can see that the critical current for the screened states on both sides is higher than the critical current in the unscreened state. Similarly, for the critical temperature, we can see that critical temperature on both sides are larger than the critical temperature in the unscreened state. And the same trend is happening also for the range of superconducting charge carriers fillings. All these shows that more screening, more superconductivity. So these were the key results in the paper, and the summary is more screening, more superconductivity. And this is an evidence for the electron-phonon coupling scenario. And this is all for this short summary. I hope you like it. And please let me know if you have any questions in Slack or maybe during our next discussion. And also, please, if you have any comments about the way I do the presentation, because I am intending to do further presentations in this style so that we have more time to discuss them later during our meetings. Thank you very much.